participants, Mr. Evan Fernandez is our leading person of the team of the Open Forum team of FOSSEE. So he'll be taking this session. So over to you, Evan. Please continue.
Yes, ma'am. Thank you, ma'am. So I'll just give a brief recap of what was done in the morning session. So in the morning, we first saw what exactly is OpenFOAM and how much development has been done since the very first version of OpenFOAM itself and how is it applicable in the field of CFD. So I'll just pass through this. Then we learned about the process of CFD. Professor Janani gave a very lovely overview of how the CFD process is. So I'll just sum it up over here in this slide. So we have first the problem definition in which we define a problem that we have. Then once we've defined a problem, we move on to the geometry and mesh creation. In this, we'll basically create our mesh that we need basically of the area of interest that we are planning on solving. Once we have done that, we move on to the solver selection. Now, this will be based on what type of equations we are planning to solve, whether it is your Navier-Stokes equation, if you have to solve any energy equations. So that way you can choose an appropriate solver. Once you're done with that, then you start setting your boundary conditions. Now, these all sections are very important for your solution and convergence because if even one of them is wrong, your solution you may not get it as per how you want it to be. So in case you have not a good mesh, so you'll have to basically go back to your meshing, refine that mesh and come back and then see your results. In case your solution is not converging, then you have to check your boundary conditions, whether you've taken the appropriate solver. So those all parameters play a big role when you are doing your CFD thing. And lastly, you move on to the post processing. That is when you have to extract any data of interest. So in case you have CLCD, so you're solving the basic force equations. And then if you want to remove the coefficients, you can do that using Python in OpenFOAM, or you can use ParaView itself. So there are multiple ways in which you can post process your data. And in these coming days, you will see how you can post process your data, visualize everything, and basically get a feel of how OpenFOAM exactly works. So this is a very basic case structure in OpenFOAM. So you have three main folders. Once you open your any OpenFOAM folder, you will have three main folders. You'll have your zero, constant, and system. So the very first folder that you will have is your zero folder. In this, you will place all your initial boundary conditions. So here you will have your velocity, pressure, temperature. Depending on your problem, you will have more files, you'll have less files. Now, in case you have a CHT case, you will have two additional files, that is a solid and a fluid. So depending on that, your files may change a bit, but this is just an overview of how your file structure will look for a basic case. Then you have your constant folder. In this, you'll have all your properties that remain constant throughout your simulation. So these can be your fluid parameters, any turbulence criteria that you're giving. So those all will remain constant. And lastly, as Professor Janani had explained this block very nicely, is your systems folder. This is where you will place your mesh, basically a block mesh dict file, your simulation parameters in which you want to change your start time, end time. That will be done with your control dict. And then you have your discretization scheme, solver settings. Those are your FE schemes and FE solutions. Now, the very first case that we have is a cavity case. Now, as you can see in this cavity case, it's a 2D case. So we have three walls. The left, bottom, and right are walls, and it's in your XY plane. And we have given basically the top wall will be moving in the positive X direction. So as it moves forward, you would have some circulation like this within this cavity. So through the very first case, we will learn to set up this case and we'll visualize how does these contours and flow parameters look in ParaView itself. And then we have the second case, that is your 2D channel case. So in this again, we have the top and bottom are going to be walls. You have an inlet and your outlet. The whole domain will be of 1 meter, and we will see how your boundary layer formation is done, and we will have a Reynolds number of 100, and accordingly we've calculated the kinematic viscosity of 0.1. Okay, so first let's begin. So this is our very first case that we have, the cavity case. So we will be starting with at basically at your 0, and we'll move all the way up to x1. That is in your x direction, we're putting it at 0.1, and the overall domain is going to be 0.1 meter. So First, we will start with our meshing. We will have basically this is how your block mesh will look. So I'll just give you a brief overview of how block mesh is working in this case because Professor Hari Krishnan already given one overview of this, and then we'll move on to the actual case. So first you will have your actual block itself. So these your whole domain will be based on these vertices that you're plotting. So basically we'll have at 0. So we have a very first point that is at coordinate system 0, that is the origin. And then at a distance of 1 in the x direction, we have 1. Of course, similarly, we have 2, 3, 4, 5, 6, 7. Okay. So in this case, the back plane that is there. So that is 0, 0, 1, 0, 0, 1, 1, 0, and 0, 1, 0. So basically this plane is your back plane. And in your x direction, we've given an extrusion of say 0.1 unit in the z direction. Okay, so your basic vertices will be set in your vertices. Then you move on to the block. Now in this block, as professor had already explained, that you place it as 0, 1, 2, 3, 4, 5, 6. Now if you have a more complex geometry, the alignment of these numbers is very important as it will play a crucial role in your x, y, and z coordinate system. So in our case, we have it at 0, 1, 2, 3. Let's take the very first four digits. So we have 0, 1, 2, 3. So when I place it at 0, 1, so I will say that it is moving from point 0 to point 1. Whereas as it moves along this direction, this will act as my x direction. Then as I move from 1 to 2, it will OpenFOAM will basically understand that this is my y direction. So my y axis is set and my x axis is set. Now, if I were to put these points as say 1, 2, 3, 4, 5, 6, 7, 0. So it would start with 1, move to 2. Then this particular axis will act as my x axis. So that's why placing these points is very important so that you will place your x, y, and z coordinate system accordingly. Okay. So once you've said that, then we move on to the boundary section. Now in this boundary section, you will basically give the faces that you have. You will basically define your faces. So in this case, we have a moving wall, fixed wall, and front and back. Now in a moving wall, the patch, as sir had basically told you, that you use your right hand thumb rule. So if my thumb were pointing outward and my fingers were curling this arrow over here, if it were curling this arrow, I would label this as 3762, just as over here, how it is written. Okay. Similarly, for the left plane, we have labeled it, if it is pointing outward, you have it at 0473. Similarly for the right and for the bottom. Okay. Now let's move to the case structure first. So first you start, as this will be a hands-on session, so I recommend that you follow along with me. And if you have any doubts, you can always stop me in the middle in case I'm going too fast or you are lagging behind or something like that. So you can always stop me in the middle because I can't really see the chat. So it will be better if you just unmute and stop me. Okay. So first you open your file explorer and you move to the left hand side. To the very bottom, you will find Ubuntu. So you click on that. Once you've opened Ubuntu, you will have home. This is where you've made your ID. So in my case, it is Infinity. Then you move on to OpenFOAM, open OpenFOAM. Now you will have OpenFOAM 9. So then you open OpenFOAM 9 and you move to the run directory. So when you were installing first OpenFOAM, that time you must have made your run directory because it was in the installation sheet. Everything is written perfectly. So you will have your run directory. So once you've entered your run directory, now most of you, if you're starting first time, you will only have one file. Now I've used OpenFOAM, so I have multiple files here, but you can just ignore that for now. Okay. So now once you're in the run folder, let's open another tab on top. So we have to copy one tutorial file. Okay. So in OpenFOAM, you don't always start from scratch. If you have a case like a cavity case or you have some simple flow case, there are already tutorials available in OpenFOAM which you can access. You can copy those folders into your run directory and modify them as per your application. Now, where can you find these tutorials? So in your Ubuntu, you go to your OPT file. Within OPT, you'll have OpenFOAM. So you click on OpenFOAM and you'll have tutorials over here. Okay. So you click on tutorials. Now for a cavity case, since it's an incompressible flow, we'll go to incompressible. and over here you have icofoam. So icofoam is basically an incompressible solver. So it's incompressible foam solver. So it's the hereby labeled it as icofoam. So you open icofoam. Within that you have cavity. Okay, so there are a few chats. Do we write 2376 instead of 3762? See, you can label it anyhow as long as you're following that right hand rule. So instead of labeling it as 2376, you can label it as 7362 as well. So that's not an issue. Okay.
Yeah, we are unable to follow. Actually, we are using this window operating system, and so how do we find these files actually?
Okay, so you are on Windows, right?
Yes, we
Okay.
are not using Linux.
No, no, even I'm using Windows only.
Okay,
Yeah.
but I was unable to find this file.
Okay, so I'll show again. So you open your file explorer
Okay.
and on the left hand side, you just
Mhm.
scroll to the very bottom. You'll have Linux. Are you able to see that?
Yeah, yes, yes, yes.
Yeah.
Okay.
So within Linux, you'll have Ubuntu. You click on Ubuntu. So we can go to OPT, OpenFOAM, and within that, tutorials. Okay. Once you go on into your tutorial file, you can go to incompressible, icofoam, and cavity. Okay. So within cavity, you have one cavity case over here. So we'll be copying this particular case into our run directory and we'll be running this. So this is going to be the very first case so that you get a feel of how OpenFOAM is. So we'll copy this. Let's right click, copy, and can directly paste it in your run directory. Paste.
Excuse me, where is the run directory?
So when you open your Ubuntu, you have home. So you click on home. Here you will have your own name written or whatever name you were making your Ubuntu, you'll have that one. Then you have OpenFOAM. Okay. Within OpenFOAM, you'll have again labeled as OpenFOAM 9 or something like that. So you open that and then you have your run directory. While installing, you must have made your run directory. Okay.
Yeah.
Yeah. Now, in this case, we've copied it into our run directory. So let's open this file. So we have zero constant and system. Okay. So the very first thing we'll go to is our mesh. So we will see in system, you have your block mesh dict. Okay. So you can open it. If you have Notepad, you can open with Notepad. If you have VS Code, you can open with that as well. So I'll open with Notepad since majority will have Notepad as well. So as I was saying, the very first you will have basically you'll have first convert to meters. As sir had mentioned, if you want to convert it to meters, millimeters, you can do that over here. Now it is set to 0.1 meters. So whatever values you set, it will by default convert it to 0.1 meter. So if I'm saying 0 to 1, at 1 it will basically 0.1 meter. So over here you specify your vertices. Then you have the block that you're basically giving a hexahedral block. Again over here the way you define these will depend on how your x and y coordinate will adjust. Then you have edges. Now in our case, we don't have any curves, so we are going to just leave that empty. And then you have the boundary. So in the boundary, you have a moving wall that is going to be the top lid that will be moving in the positive x direction. So that one we've defined over here. The face is defined. Then we have fixed walls. So in our case, we have three fixed walls. So these are defined over here. And since we have a 2D case, so we have front and back and it is set as empty. So what empty is, it's basically that in your Z direction, whatever faces are there, basically the front and back, we have taken it to be infinitely long. So that's why we've taken it as empty, that there will be no changes in that since we have a 2D case. Okay. And if you note over here, you have the number of cells. So we're giving it 20 by 20. And in the Z direction, we are giving just one cell. So in OpenFOAM, even though you're running a 2D simulation, like in ANSYS, you don't really give any depth in your Z direction sometimes if you're running a 2D case. But in OpenFOAM, you have to give a little bit of depth, not too much. And you have to just set one cell in case you're running a 2D simulation.
So I'm trying to copy that file from the run folder, but showing that I don't have permission.
Okay, so I hope that all of you are in your home run folder. Okay. So see, there are two run folders. You don't have to go into this one. Within Ubuntu, you have a home folder. Okay. You click on home. Within that, you will have one more file with your name on it. You click on that, and then you go into OpenFOAM, and within that, you will have your OpenFOAM 9 folder. You have to copy it within this run folder. Okay.
Within the open folder, having my file, having a folder named myself, but it is not having open form. It's having file as bash rc, bash history, and local, and all
Okay.
other
So
files.
yeah. So were you able to install OpenFOAM properly? Because if
Yes, sir, I have installed the open form, and
Mhm.
I clicked on the paraview in the search toolbox, and paraview also get opened, and tutorials are also visible. I
Okay.
have copied the file, cavity file.
Yes, you've copied the cavity file, that's fine. But you should have by default an OpenFOAM folder over here, because within this one you will have your, basically if you've installed properly, you will have one file labeled as your name dash 9. That will signify, basically that signifies that you have installed OpenFOAM 9. And within that you'll have either an empty folder or you'll have to make a run directory.
Yes, I will try to reinstall.
Yeah.
Maybe there's something.
Mhm. Maybe the installation is not completed properly. That's why you're not able to see this, basically this entire path.
Yes, sir. Maybe that's the case. I'll.
Sure, sure. Okay. So once we go into cavity, okay. So as I was explaining, in your blocks, you have first you define the block that you have using the points, and then you have your number of cells. So as I was saying, in OpenFOAM, even though you're doing a 2D simulation, you will just give one cell in your Z direction so that OpenFOAM doesn't throw an error, because by default it is coded to just take one cell in the Z direction if you're running even for a 2D simulation. Then we have simple grading. Now this one, as it suggests, you have a simple grading in your XYZ direction. So if you have to put any grading in that particular direction, you can put this. So if time permits, I will show you how to do this as well. Okay. So let's close this block mesh. Yeah. So once you've done with your meshing, I'll show you in the system folder what else is there. So you have your control dict. Okay. Yeah. So your control dict will basically give your start time, end time, your number of time steps you want, after how many time steps to write. So at the very start, you will have the solver that you're using. So we have icofoam. So in case you ever forget which solver you're using, you can always open this file and see the name of the solver, because the name of the solver will be very important while running your simulations. So you'll have icofoam. Then you have your start time. Now in start time, you set to start time at 0 over here. You have end time, that it will end at 0 0.5 seconds. And your delta t, we've specified it as 0.005. Now write time, we've set it as time step. Write interval, after every 20 iterations, it will start writing some files. Okay. These are all just general terms that you can see. Write format ASCII, precision you have, write compression, time, general. Okay. So once you're done with this, FV schemes, now this will hold all your discretization schemes that you're running. So now since icofoam, where it is a transient solver, that's why it is solving for Eulerian approach. And then we have your gradient schemes of Gauss linear, div schemes of basically Gauss linear, and all these. So if you ever have any problems of your solution not converging, you can always tweak these parameters to whichever suits best. Okay. So once you're done with FV schemes, I'll show you FV solutions as well. So over here, you'll have all your solver parameters. So you'll have your pressure, which solver is it using, preconditioner. If you want to put anything additional, you can always write that here. Your tolerance levels, how much you want it to, P final, then your velocity. Then over here, it is solving your piezo algorithm, that is your pressure implicit um, algorithm that you have. So here you can basically change the number of correctors you have. If you want to put any non-orthogonal correctors, you can always change this number from basically 0 to all the way up to how many you need. Your P reference cell and P value. So all these parameters are present within the FV solutions, which will be necessary in case you have a more complex problem that is not converging or something. Some problems are there, you can always tweak these parameters. So once you're done with your systems folder, we'll go to constant. Now in our case, we have Now the zone identifiers, when you copy it in Windows, you will have some additional files as zone identifiers copied. You don't really need that, so you can delete it. If you're on Linux systems, it does not really show that way. It directly just copies the files that are there. So the zone identifiers are actually not useful in any way. So you can always delete that. So you have transport properties in your constant folder. So let's open this. Yeah. So in your transport properties, you will have your kinematic viscosity of how much you want to set it to. Now over here, we'll just leave it to default. Over here, this part which is there, it will basically give your dimensions. So in the OpenFOAM documentation, if you read properly, you will find out exactly what these numbers mean. Now in our case, the value for kinematic viscosity is meter square per second. So the second one will give you your length, and the third one will give you your time. So in our case, we have meter that is squared, and we have time that is in the denominator at 1. Okay. So these will basically give you a dimension. You'll see that in most of the files that I'll show you now. So these are your transport properties. Once you're done with that, we have the 0 folder. Now within this, we have our pressure and velocity, your initial boundary conditions. So let's open velocity first. Okay, so see, as I mentioned, you'll have your dimensions. So that is given over here. You'll have an internal field. So this will basically give, you can say it will already like initialize, like if you're giving a velocity of say 1, and basically internal domain is set to already that velocity. So it will directly start moving with that velocity. If you set it to 0, it will take a very little time. So it won't make that much of a difference even if you leave your internal field as 0. But if you have like pressure, temperature, these internal fields will play a big role in those kind of cases. So as you move forward, you have your boundary field. Now in this, you specify your boundary conditions. So for a moving wall, we set a fixed value of 1 meter per second in the x direction. So you have your x, y, and z. Okay. So in the x direction, we are giving a velocity of 1. And at the walls, we are giving a boundary condition of no slip. So no slip is basically just a boundary condition saying that it is a wall, and we are not giving any, basically, if there's any flow happening on it, it will, in simple terms, stick to the wall rather than just smoothen out and just flow through it. So that is a basic no slip. You can always read about the boundary conditions for which case what is best. There are documentations on it. You can always refer to the official OpenFOAM document in which they've specified each of these boundary conditions and what exactly they do. And then we have our front back. That again, since we're solving for a 2D case, we've set it as empty. So you have U, and then we'll move to pressure. Okay. Yeah. So again, we have first the dimensions in the very beginning. You have your internal field, and then you have your boundary field. Again, over here, you have your boundary conditions, moving wall, fixed wall, front back. In this, all the cases, we've given it as 0 gradient. And the front and back is set to empty. Okay. Now, once you've just seen the overall case, how it is set up, in the next case, we will see how to change these to modify a case file that you have. Now, if you want to just run this case, since we have this tutorial, there are two ways you can run your case. You can either right click. If you're on Windows 11, it usually gives you this option of open in terminal. So you can right click and open in terminal. So once you open your terminal, you'll have to type WSL. It will take a few seconds. Then you will have your, basically you've entered your Linux environment. Now in my case, I have two versions of OpenFOAM. So I'll just source OpenFOAM 9. You don't have to do this if you just have one version. So this is how you can do it on Windows 11 if you have, and even on Linux, you can just right click, open in terminal and do this way. The second way is you can go to your search, you can type Ubuntu. So you'll open Ubuntu and you can basically go to the desired path that you've set. So to do this, first I'll just go into the OpenFOAM 9 environment. Yeah. So now I'm in OpenFOAM 9. I just type run. Okay. So it will directly take me to my run directory. That's why it is always advisable to copy all your folders that you're running into your run directory, because you can just put this one command and you will directly enter into that run command into the run directory. And a benefit of putting everything in your run directory is basically your run directory is given the permissions to run a case, modify them. Whereas in certain file structures, if you put them anywhere in your OpenFOAM environment, you may face some permission issues. So that's why it's always advisable to just keep it within your run directory. Now I've already gone into my run directory and I want to enter the cavity folder. So I will type cd and cavity. Okay. So this way I've entered the cavity case. So if I show you ls, I have 0, constant and system folders. Okay.
I'm finding problem after ls.
Okay. See, ls is not a problem. You can just, as long as you're into your cavity folder.
Okay, okay.
Okay. So once you're into your cavity folder, the very first step you will do is to generate your mesh. Now, since we are using block mesh, you will type in the command block mesh. Okay. Once you've done block mesh, it will basically generate your mesh that you've done. Okay. So it will give you some information on top, basically system block mesh. It is accessing that file and it will start running that file. So over here, you can see your bounding box points, how many points are there, number of cells, faces, internal faces. And then over here, it will give you your patch names. So we have moving wall, fixed wall, and front and back. Okay. Once you're done generating your mesh, you can start running your simulation using the solver name that you specified. Now, in our case, we have set it as icofoam because that is the solver that we're using. So once you type icofoam, you press enter, it will run for a few seconds. Okay. Now the end time is very small. That's why it is able to run quite fast.
I'm finding an error. That is, it cannot find the file.
Okay. Have you copied it within your run directory, the cavity folder?
Yes, I have.
So in your cavity folder, once you've entered your cavity folder, have you opened or gone into this folder? Like if you're running a simulation, you have to be within the cavity folder itself.
So actually, in my cavity folder, there is another cavity folder.
Okay, so if you you've copied the outer cavity folder. So just do cd cavity again. So you can just enter that cavity folder. That is the second cavity folder.
Okay, CD, then again I have to enter, no?
Yeah, you type cd and then type cavity and then you press enter.
Okay.
Yeah. Once you've done that, you can run block mesh
Yeah,
and then you can run icofoam. Okay.
yeah.
Yeah.
Nice.
So once you've done running your simulation, now we can visualize it. So we've done the cavity case. Now we'll be able to view it. You can type parafoam. It will open your para view basically. Okay. So this is one way to do. You can either type parafoam. Now there were a few people who had some errors while opening it through parafoam. For those people, I'm showing you a different way. You can open paraview.
This is showing some kind of fatal error when I am typing icoform.
Okay. Did you change any of the parameters?
Nothing. I am inside run. Inside run, I am inside cavity folder. Inside cavity, it is showing me 3 points. And so I'm in three folders: zero, constant, and system.
Okay.
After that, when I am running ICO in the small letters, F in capital,
Mhm.
OAM, icoform.
Before running icofoam, you have to do block mesh.
Okay, okay,
Yeah.
okay.
Basically, you first generate your mesh using block mesh, and then you run your simulation using icofoam. Okay. The terminal. Okay. So you type block mesh.
M is in capital. Okay.
Yes. In OpenFOAM, you'll always have the second word, first letter will always be capital. So if you have block mesh, basically the first letter of block will be small and mesh will be capital. Similar to parafoam, you'll have para that is small and F will be capital for foam. So that is the trend you can see in any of the OpenFOAM folders. Okay.
Yeah,
Yeah.
now it is fine.
Yeah. So as I was saying, you can use this parafoam command. This is the simplest way for people who are not facing any errors. You can do parafoam. For people who have problem running parafoam, that is not basically running through the terminal, you can always open it through manually opening it in Windows. For them, you'll have to just do an additional step for people who are facing the errors. Okay. So you can type touch space, and then you can type whatever name you want to specify, cavity dot foam. Okay. So you type touch cavity dot foam. So this will generate an additional file. So if I this, okay. So you see it's generated an additional file cavity dot foam. So if you're manually opening ParaView, you can then open ParaView, click Control O to open, and then you can navigate to your folder that you have kept. So mine is in basically open foam in my name, run cavity, and then you can open this cavity.foam. Okay. And you can click apply. So this is for people who are facing some errors in running Parafoam. Okay. So ideally you can directly type Parafoam and Parafoam will open. You can click on apply. On the left corner, you have apply button. Then to view your contours, on the very top part, you have VTK block color. You can click on U, that is your velocity. Okay. And then you press the play button. So now it has run some simulations, but you can't really understand what is exactly happening in this. So once you've opened your ParaView and you've clicked on the apply button, on the very left hand side corner, you'll have basically it will be set to VTK block. Okay. So instead of VTK block on this top dialog box, it's basically a drop down menu. You click on U. So you have U with a dot, you click on that one. Whereas if you have U with a cell, basically it will give you in each cell how is the velocity profile. It will basically show you that. So you can click on U with a block, it will basically smoothen out the whole thing. Now this, and then you click the play button. Okay. On top, you have the play button. Now, if you want to visualize your streamlines or you want to see some glyphs or arrows, how your flow is happening. So just below the option where you clicked for U, there's one small icon. It's called Stream Tracer. It's on the top left corner, third line. So you can click this option. Okay. So once you've clicked on this option, you scroll down. Over here, you will have a seeds and you'll have seed type. So instead of a high resolution line, you can click on point source. Okay. So it will generate this spear like thing. Okay. Now just below this point source, you will have this spear parameters. Okay. So within spear parameters, you will have radius. So you can change this radius to say 0.1. So make sure that it is covering your entire domain and that your domain is within the spear itself. Okay. So on the left hand side, you have radius. You can change that value to 0.1. And if you want, you can show spear. You can switch off the option over here. There's one small tick mark beside show spear. So if I want, you can keep that on. So I'm just switching it off for now. Below that, where you've changed your spear parameters, you have number of points, which is set to 100. Okay. So this 100, let's say we change it to around 10,000. Okay. And then we click apply. Is everyone able to change the number of points to 10,000?
Yes.
Okay.
But
So
that
once,
color gradient is not able to show.
yeah, wait. Till now, you've not done anything. We've only changed the number of points and then you click on apply.
Oh.
Okay. So once you click on apply, you will get this streamlines that you have. Okay.
Getting flat lines.
Okay. But have you changed for the point number to 10,000?
Yes, yes. The thing is,
And
when you played now, this particular thing did not play.
Mhm.
It
Okay.
did not show any color gradient.
Okay. So see, if you're on your very first time step, you can always click on this play button. It will play it and then it will give you these contours. Now,
There is some issue with the time, right? There is the time 0.5 here in there. And I
yeah,
don't have, my time is set to 1.
before opening ParaView, you type block mesh. Wait, let me just open a new terminal. I'll just open here. Yeah. So I'll just give you an overview again of what set of commands you have to type. So when you before starting a simulation or doing anything, you first go into your cavity folder. So now I'm into my cavity folder, and then you type block mesh. Okay. So you first type block mesh, it will generate your mesh. So once you've generated your mesh, you type icofoam. This will basically run your simulation and it will give you your output that you're currently visualizing in ParaView. So once you're done with icofoam, it will run for a few seconds and then you type parafoam. Okay. So this way you'll be able to visualize that whatever you've solved. Okay. Okay. Yeah. So now we've plotted our streamlines. Now, if you want to better understand, or if someone is first time learning something in OpenFOAM, or if you want to just show them how the flow is happening. So in that case, you have another option. So there's a small I option on the left hand side where your file names are there. So you can switch on and switch off. So I will switch off Stream Tracer for now. So as I was saying, if you want to just show how the flow is happening with arrows and everything, so there's an option called glyph. So just where you switch, basically you switch to your cavity case. Again, where you clicked your stream tracer, just beside that, you have a glyph option. So you can click on the glyph option. It's over here, just beside your stream tracer. Okay. Now in your glyph options, you'll have orientation and scale. Now orientation, we can switch to U. Basically, all the arrows will orient itself how the flow is happening. So in our case, it is taking the velocity profile, however the velocity is flowing. And in scale, you click on no scale for now. I'll show you why. So if you click on no scale for now, and I just click on apply, okay, it will show me how my flow is happening. So you can see on top, as the lid is moving, you have some flow that is the region closest to that lid. It will start to move, then it will hit this wall and it will start to circulate again inside this. Okay, I'll let you see it properly. Yeah. So you can see over here, you have this kind of flow. Now, the reason why I said to switch off the scaling factor is because if you switch on the scaling factor and you set it to U and you click it to apply, the arrow size will change according to the amount of velocity that it has. So over here on top, you will have the highest amount of velocity or the highest amount of flow. And as you move farther from that, you will have less flow. So you see the arrows also are getting smaller as it moves away. Yeah. So if you change the scaling array, it will basically change the size of your arrow based on the flow intensity. Okay. So is everyone able to understand till here and able to execute till here?
Glyph option, could you please repeat?
Okay. Okay. So I'll delete the glyph option. So suppose you've opened your OpenFOAM and you have your cavity.openfoam file. Okay. So just below this option where you clicked for U, you had the stream tracer option, and beside it, you have a glyph option. Okay. So you click on the option beside it that is labeled as glyph. So you click on glyph, and over here you will have some options over here. So you have orientation and scale. Okay. So in orientation array, you click on this drop down menu and you click on U. Okay. And once you clicked on U, you can click on apply. So it will generate these arrows that you have. Now for you to better visualize it, if you look closer to the lower end, you'll have another option called coloring. Now the coloring will be set to U. You can click that to solid coloring. It will give you white arrows. It will help you better see the whole thing. So this way you can see the arrows and the flow happening. In case you want to change the arrow size based on the intensity of the velocity or pressure, if in case you want. So over here you have scale option. You can click on scale and you can set to U and click on apply. It will basically scale your arrows based on the intensity. Okay. Yeah. And someone else also had a doubt.
It's okay. I was
Oh,
having gilf only.
okay. Okay.
Glyph.
Yeah. So is everyone able to do so far?
So I've done exactly what you're trying to do. I've done everything. But
Okay.
what happens is that the problem physics is completely different for me.
Okay.
So it's what the physics is completely different. I'm getting a different kind of simulation.
Okay. So wait 1 second. Yeah. So is your simulation something like this?
Yeah, sort of.
Yeah. So on top, once you've selected or you try to run your simulation, there are these options. You have a play button, then you have one back button and all that. So click on
Yes,
the
sir.
play. Yeah. So click on the play button.
Yes, sir.
Now are you able to see the whole thing properly?
Yeah. So the simulation is running. There is
Mhm.
some sort of distribution is happening. But
Okay.
what is happening is that the physics is completely different. The core idea of the problem is completely different from the what are the results I'm getting is completely different. That is a concern I'm having.
Okay. So what exactly are the results that you are getting?
Mm, since there is a distribution in the downward, right? I'm
Yes.
getting a distribution in the center. After that, it stops. Then there is no like the contour you're getting is completely different. Out of the contour I'm getting,
Okay. Okay. Are you getting something like this?
not I'm not getting that.
Okay. So you're having problem with streamline or glyph?
Streamline itself, I got a problem.
Okay. So your streamlines are also not matching this way.
Yes, yes, sir.
Okay.
So the procedure and everything I understood, but the results are completely different.
Okay. So did you change any of the parameters in your zero folder?
No, I didn't change anything.
Okay. So now this is just a base tutorial. That's why we're just giving you to understand how OpenFOAM is. So even if the
Okay, sir.
results don't match accurately as like to
Mm,
mine,
oh,
it's fine
Okay, okay,
because we're
sir.
not trying to validate anything here currently.
Okay,
Okay.
okay, sir. Okay. So trying to match you, that is what the problem.
Okay.
The other thing is that so this is all fine, sir. There is a can you people teach us to how to write this particular script?
Script as in?
As in, like these are tutorials. So everything is ready.
Yes, yes.
Everything's ready. We just have to go put the prompt, and the prompt is giving the mesh, and prompt is giving the analysis and all.
Correct.
So is there any session for us to write the prompts?
Yes. Now in the next session, we'll just show you how. Now this one was copying a case and running it. Now we'll show
Okay,
you how
sir.
to just modify it a bit for the
Okay,
2D
sir.
channel case. Okay.
Okay, sir. Okay, sir. It's okay, sir. I'll follow it up. Okay,
Yeah.
I'll try to match you.
Yeah. Fine.
Uh,
Yeah.
yeah, there was this query like we want to see the data in tabular form. So can you just navigate to that option in
Okay.
Paraview?
Yeah. So suppose you have velocity and you've played. Okay. Now this data, if you want to extract it into some other, like if you want to plot some options. So wait. So on the left hand side, you have this render view option. Just beside it, there's one small icon that looks like a splitting option of window. So you can split horizontally. You click on that, it will basically give you two windows. And on the left hand side, it will give you a set of options. So at the very bottom, you see there's a spreadsheet view. So you can click on spreadsheet view and it will give you all the data that it has plotted. Basically, what we are visualizing, it will give it to you in a tabular data. Okay. So suppose you want to export this data out. There's this option over here on the right hand side corner, export spreadsheet. Okay. So you can click on that and it will export your file in a .csv file. So suppose I label it as export. Okay. File name of mine is export. It is going to export it within your file structure only that you set. So it will be exported. So if I refresh it, so you see in your file structure that you have already, you'll have this export.csv file. So this CSV file, you can open it in Excel and you can basically, if you want to plot something additional, you can do that over there. Okay. So now this was just copying a simple cavity case and running it.